Hello everyone. I am presenting our work Disentangled Pose and Identity in Semantic Image Manipulation or Dispositioned on behalf of my colleagues. Semantic scene graphs are graphs that describe a scene. To the right you can see an example of such scene graph. The nodes in the graph are objects in the scene, and the edges are the relationships between the objects that can be based on, for example, an action such as holding, eating, or based on proximity, that is near, left of, or based on support or comparison. The nodes in the graph can have attributes such as object properties, which could be based on color, shape, or material. In this work, we propose a new method for semantic image manipulation. Image manipulation can be useful for generating novel scenes, and semantic editing enables changes in the semantics of the scene, which could be, for example, the relationships between the objects. To the right, you can see two examples of such changes in the scene. For example, in the upper image, we change man riding the wave to man near the wave, or in the lower image, we change person sitting in the sand to person standing on the sand. SEMSG, or semantic image manipulation using scene graphs, was proposed recently for the semantic image manipulation task, but this work has some limitations. SEMSG learns entangled latent embeddings, which can cause problems in the generation of the new object instance and preserving the object features and the appearance of the object when doing specific changes such as relationship changes. And it also has low diversity in the generation of new instances. We propose a new model for this task, which could learn disentangled representation, and also using variational latent embedding, it generates images with higher diversity. So our main contributions are a self-supervised approach for the disentanglement of pose and appearance for semantic image manipulation that does not require any label information for the disentanglement task. We propose a disentangled scene graph neural network and also a variational latent representation using variational autoencoders that enforces higher diversity in the generation of new instances for image manipulation. Our method achieves superior quantitative and qualitative performance compared to the state-of-the-art on two public benchmarks. In this figure, you can see an overview of our method. The training happens using a proxy task based on reconstruction of the image from the scene graph and the input image. So during the training, we randomly mask part of the image and the same scene graph corresponding to that image and try to reconstruct the masked image. And at the test time, we perform the manipulation by masking the specific parts of the image or scene graph or the object features based on the manipulation mode. The disentanglement of features happens in two parts. In the first part is using the disentangled scene graph neural network that processes the features from the scene graph and enforces disentangled features extracted from the graph by using neighborhood routing. And the second disentanglement part is done through a variational autoencoder. We have two variational autoencoders. One encodes the features for the appearance of each object, and the other one encodes the pose features. And we have a decoder. The decoder of the pose encoder tries to predict 6 parameters that correspond to the to affine transformation parameters. And from the appearance encoded features, we predict bounding box and pseudo segmentation maps. and then these are combined to create a scene layout, and then we feed this scene layout to the appearance decoder that gives us the final image. You can see a graphical model of our method here and also the objective functions. The model is optimized using a combination of different losses, which are the variational loss, the generative loss, and the bounding box regression loss. Our method is trained and evaluated on two public benchmarks for scene graphs, which are Visual Genome and Microsoft COCO. We evaluate our model qualitatively on three manipulation modes, which are object removal, replacement, and relationship changes, and also evaluate it quantitatively through the reconstruction task and report the FID, inception score, LPIPS, MAE, and SSIM values. We compare our method to two state-of-the-art methods for semantic image manipulation, which are interactive scene generation and CMSG. In this table, you can see the image reconstruction performance of our model on Visual Genome. Since we don't have access to pairs of edited images before and after the editing for the image manipulation task, the evaluation is done through the reconstruction task, where either the whole image is masked and reconstructed using all of the methods, which is the first part that we call generative, or random parts of the image are masked and reconstructed. And we can use either ground truth graphs to perform the manipulation or the reconstruction, or predicted scene graphs. As you can see, the reconstruction performance of our method compared to both previous work is superior, and it achieves the best performance among all. Here you can see the image reconstruction performance on COCO, which is consistent with the results obtained on the Visual Genome dataset. And we also perform a user study on Visual Genome to compare our method in semantic image manipulation to CMSG. And we also provide an ablation study of our method on Visual Genome by either using the disentanglement only in the latent embeddings of the model or combined with the graph. And we show that both of these disentanglements are effective and can improve the performance of the model. Here you can see some qualitative results of our method on three different manipulation modes on the Visual Genome dataset. These manipulations are either relationship changes or object replacements, where we replace an object with another object, or object removal. You can see some examples, and if you look, you can see that the new generated images have higher quality from our method compared to CMSG. For example, if you look at the replaced objects in the middle column, the generated person looks more realistic. And if you look at the relationship changes, the generated image or manipulated one by our method represent the specific scene change better and also preserve the appearance of the person better. And here you can see some qualitative results on COCO dataset, which is again consistent with the previous results. To conclude, we propose a novel disentangling framework for image manipulation using scene graphs. The disentanglement is an effective way to improve image generation and manipulation quality. And we show that the variational representation for object features enables generating more diverse images compared to the previous work. And also the disentangled graph neural network extracts more meaningful and useful features from the scene graph, which results in higher reconstruction performance. Thank you for your attention, and we look forward to the discussions in the poster session.